Hello students, in this session let us solve this question of columns. In this question it is given that 800 long straight bar of alloy steel and of 10 mm by 4 mm section is mounted on a strut testing machine and loaded axially. The load is increased till the bar buckles. Determine the maximum central deflection before the material attains the yield point of 300 megapascal. Assume the Euler's formula for pinned ends E equal to 75 gigapascal. So this is a question of columns where we are given with the length is given 800 millimeter long steel, that is alloy steel. Alloy steel bar is there. The cross section area is given 10 mm by 4 mm. It is loaded axially on a testing machine and the bar buckles at certain load. We have to determine the maximum deflection in the beam, that is delta, the maximum deflection, before the material attains a 300 megapascal of stress. The maximum stress is given 300 megapascal. We can assume that both the ends are hinged. Pin ends means both the ends are hinged, and the modulus of velocity is given 75 gigapascal. So let us solve this problem. Hello students. In this question we are given with a pin joint alloy steel bar which is working as a column or strut. This is same thing, and it has a length of 800 mm. You know that for pin joint or hinge joint, when both ends are hinged or pinned, the length or effective lengths are same, right? So we will use the same length in our Euler's formula or crippling load formula. And it is of cross section 10 by 4. The depth given is 4 millimeter and the width is 10 millimeter, right? And maximum allowable stress in the material is 300 megapascal. So the stress should not exceed this limit, 300 megapascal. Modulus of elasticity of the material is given 75 gigapascal. We have to find out this deflection. The deflection is maximum at the center. At the center point, you can see here, due to symmetry, the deflection will be maximum at the center. We have to find this deflection, delta, right? That what is the value of delta? We know that crippling load or Euler's load is given by the equation that PE equal to pi square EI upon LE square, effective length. Here effective length and total length is same. But what is I? How to use I? Moment of inertia. So we have two moment of inertia, about XX and about YY. So we have to calculate both moment of inertias, IXX and IYY, and we will use the minimum moment of inertia because the failure take place about the minimum moment of inertia, right? So first of all find IXX. IXX is BD cube by 12. So B D cube by 12. Solve it and get the value of IXX, BD cube by 12. So this will come out to be 53.3 millimeter 4. Similarly, find out IYY. Now for IYY, this is the axis. This is the axis, and it is perpendicular to B. So it will become B cube. So DB cube, right? DB cube. So this is D as it is and B cube by 12. So IYY now come out to be, solve it and find the value 333.3. 333.3 millimeter 4. From these two values we can conclude that IXX is less than IYY. So I minimum is basically IXX, which is 53.3 millimeter to the power 4. So I minimum is basically IXX, that is 53.3 millimeter to the power 4. So this is our moment of inertia to be used in this formula. This is our main formula of Euler's load, right? So we will use this moment of inertia in this formula because this is the minimum out of these two, right? So it is okay, we have found out the moment of inertia. Now what is the stress? What is the stress? What are the stresses developed in this material? There are two types of stresses developed in this material. One is a direct stress. Due to this P, the direct stress will be developed, that is force upon area. And another is the bending stress due to this bending of the beam, right? There are two types of stresses, right? So there is direct stress, sigma D, that is basically load upon area. And another is bending stress, that is equal to, you should know the formula for bending stress, that M by I equal to sigma by Y. M by I equal to sigma by Y. So from this formula, the bending stress will be, here this is bending stress. When we are saying sigma, it means bending stress. Sigma B will be equal to My by I. My by I. So these two formulas are there, My by I and P by A, right? Now, what is P then? What is P? How to find out this P? This P is in this formula. You can use this formula to find out the load P, which is given by the Euler's load. P is given by pi square E is given to us 75 gigapascal. Gigapascal become Pascal by multiplying 10 power 9. I moment of inertia 53.3 millimeter to the power 4. So this will become minus 12 when we convert it into meter to the power 4. 10 power minus 12 divided by LE square. L is 800 mm. This is 0.8 basically square. So from here we can find out the safe load of this beam, that is pi square E I upon L square, right? So what is safe load? That will come out to be 61.7. 61.7. So this is 61.7 Newton. So this is the safe load, Euler's load for this equation, 61.7, right? So we have obtained this. So P is obtained now. This P is obtained, Euler's load or safe Euler's load. So sigma, now the total stress will be, sigma max will be equal to sigma D, direct stresses plus bending stresses. Two types of stresses are there, and the maximum stress is given to us, that it should not exceed 300 megapascal. So maximum stress is equal to direct stress plus bending stress. So put here sigma max will be equal to, direct stress is load upon area, so this is load upon area, plus bending stress is given by My by I. My by I. Now load is known to us. What is area? Area is B into D. This area, B multiplied by D. So B multiplied by D plus M. What is M? We are talking about the central point where the deflection is maximum. So maximum bending moment will be here only. That is P multiplied by delta. So M will be equal to P delta. This is the maximum bending moment, which is the deflection at the center. So this is P is known to us, delta. Why? Now moment of inertia, the moment of inertia minimum is this. Minimum moment of inertia is Ixx. This is the minimum moment of inertia, right? So in this case, if this is minimum moment of inertia, then this is the value of y, because y is the topmost point, the distance of topmost point from the neutral axis, and we are taking this axis, right? So this is d by 2 basically. This will be equal to d by 2, right? So this is d by 2. So y is basically d by 2 divided by I. Minimum moment of inertia we have already used, bd cube by 12. So this is bd cube by 12. So from here you will get Euler's load divided by bd plus, here you will get 6 pe delta upon bd square. 6 pe P delta upon B d square, right? So this is the sigma max. This is the sigma. So sigma max we have obtained. Sigma max we have obtained load upon area plus 6 load into deflection, that is movement, upon BD square. BD square. So this is our sigma max. From here, all the things are known to us. The only unknown is delta, deflection, which is deflection at the center. So from here we can find out deflection. Sigma max, put the value of sigma max 300 megapascal, use in megapascal. So megapascal, P is known to us, P 61.7, divided by area. Use area in millimeter square so that you get the value in megapascal. So 300 megapascal and divided by area in millimeter square to get the megapascal. So 10 multiplied by 4. So area is 10 multiplied by 4 plus 6 PE. P is again 61.7. Delta need to be find out. The answer will come in millimeter because we are using all millimeter values. BD square. B is given to us 10. D square is 4 square. Now here in this equation only one unknown is left. And what unknown is that? That is delta. So left side is known to us. This is known. We can calculate. These things are known. Only delta can be calculated out of this equation, right? And finally, you will get the deflection. Deflection in millimeter you will get as 129 millimeter. 129 millimeter. And this is the answer of this question. So this is the answer to this question, 129 millimeter. So how we solved this question? We are given with a column which is pinned or hinged at 2 points. We have to find out the maximum deflection when a safe load is applied. How to find out that safe load? Using this formula, Euler's formula. Using this formula we have found out the safe load which can be applied here. And due to this load, what is the deflection at the center, which is maximum, we have to find out, right? So in this formula, I minimum we have to use because the failure take place at the minimum moment of inertia. So out of Ixx and Iyy, we have selected the minimum moment of inertia, that is Ixx, which is this. Now, due to bending and due to direct stresses, two types of stresses are developed. This is one is direct stress, that is load upon area. This is the direct stress, and another is the bending stress. Bending stress obtained from this formula. Is this formula my by I, right? This formula or this formula, m by I is equal to sigma by y. This is the bending formula. From here we have obtained the bending stress. So direct stress and bending stress and it will give the combined effect will give the maximum bending stress, maximum stress, and maximum allowable stress is 300 megapascal. This is given to us. So this maximum stress is equal to direct stress plus bending stress. So put the values here and you will get the deflection, and the deflection is basically movement is the load multiplied by deflection, and by this we found out the deflection. In this question, one more thing you can think of is, you can see here that this 300 is composed of two parts, direct stress and bending stress. When you calculate this will be very small quantity compared to this, because this is a long column, and long column generally fails in bending and not in direct stresses. We have taken the combined effect of bending and direct stresses, but for long columns we can safely neglect this value, and we could have directly used 300 equal to this value, and we can find out delta, right? But in this case we have included direct stress also, although it is very small compared to this. If you calculate it, you will get that this is very small and this is very large, because failure take place with bending. But we have included this also. This will give the accurate result compared to neglecting this quantity. So we could neglect the direct stresses because failure take place due to bending in Euler's formula. But this is also a good question.